we can. So this week is the second last one. And the topic is, as you can see here, the basics of decision trees, both for classification and regression, and so-called ensemble models. So ensemble models is essentially you growing a forest. So it's an ensemble of trees. And there are different types of trees and forests which we will grow. And there are some videos which you can take a look at here. And I'm going to actually repeat a little bit of what we discussed last time. And the whole topic with decision trees is that this allows us a very intuitive way of making, for instance, a classification problem. So the typical tree is to split the tree into the predictor space into distinct and non-overlapping regions, like we discussed last time. And for every observation that falls into that region, we make the same prediction. So if you're dealing with a regression case, we would typically split a region into smaller regions. And the prediction we make then is the average value of the observations we have in that specific region. Then that means that you can narrow down the number of observations in a specific region till you just have one observation. Then your prediction is actually that point. So that tells you quickly that decision trees lead to overfitting, because you can really make a perfect fit to all the data points. So let me just quickly remind you of some of the typical examples which we saw last time. And last time when we looked at the typical decision tree, if we now go into this file with the results, not that one, but the other one, data files. So one of the typical things which we can do with scikit-learn, for instance, is to generate a figure of all the different features which we have. And this is back to the data which we had on cancer, the Wisconsin breast cancer data. And what we did last time was to use a typical binary splitting. So we would split the tree into first a root node, which is the most important feature. And when we run the classification here, we get this worst perimeter. And then we found a Gini factor, which is the way to express the most likely feature. And based on that one, we could have true, false. And then we see now that we have, of the training which we did, we had 269 true cases. That means that the worst perimeter is smaller than 106. So this is something which has a meaning to a pathologist, obviously. I don't know what the worst perimeter means from a clinical point of view. And then you can keep splitting this. So at the end, you have what we call the leaf nodes. That's the end of the different branches. And there you see you have this Gini factor, which is a measure of the purity. So a Gini factor equal to 0, or entropy, which is another measure of purity. When that one is 0, it means that that specific leaf is populated by only one class. So you can then build this tree, and you see that immediately this is something you can bring to people and say, look, if we are dealing with cancer treatment, this model tells us that the worst perimeter is the most important feature. That's the one we should look at first. And when we have looked at that one, we have this true false. Then we can look at what's called the worst concave points, the worst texture, etc., etc. And this brings us down to the final set of features. Now, this is not as detailed as we want to have it, but in general, this is the kind of things which you can get from scikit-learn, for instance, when you plot the tree. Last week, we looked at this case with grades. And I'm coming back to this figure a little bit when we have done the grade case again and reminded you of that. So in that specific case, this X0, this what it does, I haven't put any labels on it. So you have to go back to your table. So X0 was the data set on the grade trend. And in that case, what we found last week was that if the grade trend is below average, which is true in that case, so below average, true, then we found that we had 4 samples, and our tree, when we looked at a grade trend, which was below average, and how that correlates with the final grade, then we found that we had exactly 4 cases, and that had a Gini factor equal to 0. Then if we go false, that means that the grade trend is above the average. What we found then is that this variable x2, which corresponded to the number of hours we studied, that was the second most important feature for the final grade. So what we did was to have a simple classification problem where we looked at 3 features: the grade trend from previous exams, the number of hours we slept, the number of hours we studied, and then clearly the output was the final grade, whether that was below or above for a specific exam. And what we find then is that if the grade trend is below the average, then we have a case true where all the grades are below average for that specific exam. And that terminates the tree leaf or the branch. So normally we would have something which is called the root node, which is the first one. And then we have the an internal node like this one. Now here, when we terminate with a Gini factor equals 0, which is a measure of purity, when the Gini factor is equal to 1, that is a measure of the most unlikely case. So we want to have a pure case, obviously, and that's where the tree terminates. So in our case, we have 4 cases with grades below, which correlates the grade trend with grades below. And then the next one, where we have false, the internal branch here, is the case where we have a number of hours studied. And in that case, what we have now is that this branches into true false. So this is below 0.5, so that below average or below high, well, as we defined it last week. And then we see that now we have, in that case, we have only 2 samples where we get a grade below. And then we have a Gini factor here, which is also pure, where the grade is above. So this is the way we would now present the tree, and we would say that the grade trend, if you want to interpret it, if you go back to what we did last week, the grade trend is the most important feature for the final grade. Then the hours which we study is the next important feature, and that's where the tree terminates. So the number of hours we slept in the kind of data set which I put up, this is something, remember now that this is something I made by hand. This data set is a data set which clearly correlates with the number of hours studied and the grade trend. So that this is a typical example of a tree which we would get when we run this type of analysis. So let me just bring back my Jupyter notebook. So I'm not going to repeat everything here, but what I wanted to say when we have gone down here with a typical classification tree, what we did was to split the tree in nodes in the classification case. The regression case is not that different, and we would typically define a probability, which is now the observation of a given class in a given region with a given number of observations. Then you could use something which is called the misclassification error, which is less used. So what we did was to use this Gini index. And that's the quantity we use from the example last week to split the tree in a binary way. This is the most common algorithm for constructing a decision tree. And the algorithm is called the CART algorithm, where CART stands for classification and regression tree. So we have 2 measures. One is a Gini index, and the other one is the entropy. Normally, people tend to use the Gini index because that avoids the calculation of a log. If you often train a tree, calculating the log requires more cycles. But these are 2 measures, the most used measures in splitting the tree. And then clearly, if you have a tree or a leaf where the entropy or the Gini index is equal to 0, that means that terminates the internal branches, and it becomes a leaf branch, or just a leaf node, as it's called. So when we use scikit-learn, actually, we can, as you could see, we can set up this way to perform a printout of the results. So here you see an example of where we load the breast cancer data, and we have taken the breast cancer data, we perform the standard train test split, we use a decision tree classifier, and then a tree has a parameter, and that is the max depth of the tree. So that means that you make at most 5 internal nodes, including the root node. So in that specific case, we have decided that we want at most that amount of nodes. You can make the tree deeper and deeper. That means that the tree becomes more expensive to train. And when we are going to these boosting methods, what we are going to use is a shallow tree, a tree with a very small depth, because we are going to use that as a weak learner. And we are going then to use these boosting methods to actually improve upon the quality we get from just starting with a weak learner. So it's just you starting your approximation with a linear polynomial for your regression type of problem, and then you keep improving upon that. So we are coming back to the boosting methods. These are extremely popular methods for training either regression cases or classification problems. So in scikit-learn, you can include things like this export graphics. And in that case, you produce these files, which I showed you. So you produce a so-called dot file, and then you keep on going, and then you would produce this cancer figure, which then gives you the final tree. So I'm not going to go through all these examples, but these are just examples on how you can actually run it. One way you can, if you run these cases, let me just run through them, and then just take that one. So you can plot the tree directly if you want, like this. So this is another possibility. So scikit-learn allows you to plot the tree, and then you would have to save that figure in some way and use that as the way you present the data. But you can also take a tree and you can print it out as text. And this is given by the export text option here. And this is the iris data. So that says that the petal width less than 0.8, then class 0. And then you have to retrace back what is class 0, class 1, and class 2. So these are typical examples on how you can print out the information about a decision tree. Now, in the slides here, what you will also find are the classical algorithms. And one of the standard algorithms which is widely used is actually this CART algorithm, which stands for classification and regression tree. That's the most used one. So if you're dealing with a classification case, what you typically do is that you split your data into blocks, and then you have the block to the left. You do the counting of the number you have to the left. You calculate the Gini factor, and then to the right and to the left. And then when you have successfully split the tree set in two, then you split it in new subsets where you use the same logic as we discussed last week. So the example from last week, which is the one we had, if you scroll down, I'm going to come back to these slides here. So if you look at the example we had last week, this was given now by the grade trend, the hours slept, the hours studied, and then we had the final grade here. And then the tree which we then constructed was the one which we showed just right now, where this x0 was the grade trend, x1 is the hour slept, x2 is the hour studied, and we found that the grade trend and the hour study were the most important features. So typically what you do when you do these calculations is that you translate all classes into numbers, and in the code which you saw here, you would find then all my data sets. If we just scroll down a little bit, you would typically find the data sets given in terms of just numbers like this. So here I'm hard coding the data set. So you would typically translate it into numbers. And if you have more than one class with a specific feature, then you could have numbers from 0, 1, 2, etc. And the case which you see here is an example of another data set. And you see now that you have this different, for every main feature, like the outlook, you could have sunny, overcast, rain, and then temperatures just hot, mild, and cool. So you would have more than just the grades which we put where we had just above or below. So when you're encoding this information, you would typically encode this information as a given number. And then you would use that in the classification problem. So if we go back a little bit here, when you now are computing these or making the tree, you would typically use this CART algorithm, where you simply now count and compute for the regression case, the mean squared error to the left block. So in the beginning, you take your data set and you split it in two. And then you would center it around the middle. And then you would pick a given number of data to the left and to the right. You would calculate the mean squared error. And then when you calculated the mean squared error for a specific node, then you would simply keep going till you have subdivided into as many nodes as you have this, or as many regions as you have decided. And then your expectation value or your prediction is the average value of all the points in that small region. So you would do similar things with the classification case, except that there you would set up the calculation of the Gini index or the entropy. But for the regression case, you take a big region, you split it in two first, and then you calculate the mean squared error for each region. And then your prediction then is given by the average value. And then you keep splitting this into smaller and smaller regions till you have reached the max depth for the tree which you have defined. So it's custom to actually split a tree using this binary split. And the reason is that these multi-way splits fragment the data too quickly and leaving insufficient data and at the next level down. And multi-way splits can be achieved by a series of binary splits, and this is normally preferred. So when you compute the Gini index, the example which you see here is the same one which we went through in detail last week. So I'm not going to repeat the way we went through it last week, because you have in the lecture notes here, you also have a link to the whiteboard notes from last week, where we actually went through a detailed calculation of the Gini indices. So I hope this is more meant as a kind of repetition of the decision trees we discussed last week and how to make one. So what we are going to look at now, I'm going to skip this, how you actually set the Gini factor. So there are codes examples where you actually set up the Gini factor, but I will not be running them because it's not that interesting unless you want to write your own code. Normally, what we end up doing is to use the functionality which scikit-learn has. This is my basic recommendation. But you will find code examples where actually do the calculation of the Gini factor. You can use these if you want to write a program yourself. And we've always had people for the third project who have written codes for decision trees. However, what most of you end up doing in the final project is that you take the optionalities and the functionality of scikit-learn, and you simply use that one to make your decision trees and more advanced models. So typically here, when you use a decision tree, the typical way you would set it up now is you would initialize things randomly, and you have a regression tree, and then you define a max depth equal 2, or you can make one with a max depth equal to 3. And if you run, I have to rerun some figures here. Let me just rerun some of the codes here. As I had. So this is a typical example of the results when you do a max depth equal 2 and a max depth equal 3. So we have these random points here, which we want to fit with a decision tree. And you can see now if you have a very shallow tree, then clearly your prediction is not the best one. But if you have a max depth of 2, for this specific case, what we have done now is that we have split the regions into 3. One region here, one here. This is to the this will be the tree with a depth 1. And then you see now that the prediction which we're making is not the best one, because the prediction for this region, which you see here, is the one which is given by the average value. So the prediction we would make here in this region is given by this line. In this region here, in the center region, it's given by this line. And similarly, in this region, this is the prediction I make with a tree of max depth equal to 2. If I make a tree of max depth equal to 3, that means that I have at most 3 internal branches. Then you see now that I'm subdividing the regions into smaller and smaller regions. And then my prediction is the red line, which is the average value of all the observations in that specific region. So this is how a regression tree works for a regression case. And your prediction is then the red line. Now you can then increase this, and now you see clearly why using decision trees can easily lead to overfitting. Now you see I have basically no restrictions. I make a tree where I have the minimum samples leaf is equal to 10 here. So I require at least 10 observations at most in each region. If I have no restriction, you see now that my tree is roughly trying to go essentially through every point. So this figure which you see to the left here is a typical case of a situation where you will end up with overfitting, because this is your training data. And if you then fit a model to basically reproduce all the training points, as you can see in the figure to the left, then clearly the prediction you will make on data which was not included will very likely lead to overfitting. So trees are extremely simple to understand, but they also have they have the power of giving a perfect fit. But the problem is that you may easily end up with a tree which overfits them on the data which was not included in the training. So you can make restrictions like this, mean samples in leaf, which means that the minimum value of samples in that specific region is 10. So you can you have several options. You can decide the max depth of the tree, and you can also decide how many points, observations you want to have in a specific region. So these are typical functionalities which you will have when you use scikit-learn. And you can see that these are options which you can put in here. If you don't put in anything, this leads to this unrestricted tree. And then it tries to find the optimal representation of your data. Now, when you're running Project 3 and you want to make comparisons with different methods, using decision trees or ensemble methods is something which we always recommend. So suppose now you do a classification problem and you run with your neural network code. You can run with a logistic regression code, and then you have at least 2 methods which you compare the results with. But then having a decision tree or random forest and so on, using scikit-learn makes it much easier, and it gives you a broader spectrum of methods. So it's very common when you run machine learning algorithms for a specific problem that you test more than just one method. And typically with the functionalities you have here, like with scikit-learn, you see how easy it is actually to set up a fit with a decision tree. Then I would typically recommend to study decision trees as well, or ensemble methods. These are very easy to include. And it doesn't take that much time either to run with many of the data sets which you have picked. So one of the nice things with decision trees, there are pros and cons. It's not a black box. It's actually a white box. It's you who decides how deep it should be. It's you who decides how many points you want to have in a region if you're dealing with a regression type of problem. It's you who decides how deep it should be also for a classification type of problem, which means that it's easy to interpret. And many people actually think that they actually mirror human decision making. So in this kind of true false, if you think back of this game which you played, which we mentioned last time, when you were kids, you would typically play this game with 20 questions. And you were sitting in the car with your parents on a long trip, and somebody would guess a specific thing, and then you had 20 questions to narrow down and nail down what that thing the person was thinking of is. And a decision tree is very much like that. So it gives also a very easy thing to interpret. There's normally no feature normalization which is needed. You can deal both with continuous, you can do classification and regression, and it also can model nonlinear relationships, and it can model interactions between different features. So it doesn't need to have homogeneous input data. And you can display them graphically, which makes it very handy. So this is something you can show to your friends. Here you see what the decision tree gives us when we train on this and this data. However, normally the trees do not have the same level of predictive accuracy as some of the other methods which we have encountered. You need to make the tree very deep, but then you can easily run into overfitting. So if you use continuous features, the tree may become quite large and less interpretable. So if you're trying to fit a continuous function, you can actually narrow down smaller and smaller region, where at the end you have just very few observations, but then the tree is difficult to interpret. And the same applies also if you have many features like the cancer data. The example I showed you was a tree where we stopped at level 5. So we had at most 5 internal nodes. You can make it deeper, but then it becomes much larger and more difficult to interpret. So there are many pros and cons when you run with trees, and you can read some of these things. So if the number of features is relatively large and the number of instances is relatively low, the tree might overfit the data. And then you have features with many levels, maybe preferred over features with less levels, since for them it's more easy to split the data set, such that the sub-data set only contain pure target feature values. There are many different pros and cons. And this has led to the jungle of methods, or the forests of methods. And hopefully, since we now are staying with this forest and tree kind of world, I hope you will see the wood for the trees. I've probably heard this many times now during the semester. One of my favorite sayings. And the methods which we are very popular, one which has been around for many years. One is just a voting classifier. So there's a very, this is just based on statistics. So you can take a majority vote, or you can take normally a vote which is called a plurality vote. So the majority vote, you simply take the feature which gives the most outputs, and that is the majority vote. And that's normally used in a binary system. But if you have more features, you would typically take the sum of the different probabilities. So a typical binary case leads to a majority vote. So you think of you tossing a coin, right? Now, you know that if you toss it 10 times, the likelihood for you to have a perfect 50-50 case is not very high. There is I don't know if you've seen this in statistics, but there is a way to calculate the likelihood of getting a 50% score. So let me just quickly remind you of that likelihood, if this is something which may not ring a bell here. So let me bring up the whiteboard. So think of you tossing the coin, and you do it 10 times. And then you ask yourself, what is the probability of having a perfect 50-50 case? So that probability is something which, for those of you who may have taken a course in statistics, this is now given by, so if we now write a probability, sorry, not that one. If we write the probability of a given event, which we call x equal to k, let me just write this down. This is given by something which we call the binomial factor. So 10 could be the number of coin tosses, and k could be the precise case we want. We want 5 of the tosses to be coin and 5 to be head, not tail, head or tail, right? And this is now given by a probability of a half. So 50% is the probability of head or tail. And this is to the power of k, and it's multiplied with 1 minus a half to the power of n minus k. And clearly in our case, if we now put k equal to 5 and n equal to 10, then this is going to give us the factorial of 10 of 5 times 5 times 1/2 to the power of 10. So that's a probability of a perfect fit. Now, if you're not having a perfect fit, then in this specific case with these numbers, suppose now you want to say, what is the probability of having at least 50%? So you're not asking for the precise probability, but you're asking for at least. So that means that we would have something like x larger or equal to k. Actually, it's larger than k. That's larger than equal than k. And that would have a summation which goes from k plus 1 up to the final value. And then we have n of k, and then we have 1/2. In our cases, with the probability is 50-50, then this is simply just 1/2 to the power of n. Now, this is something you may find in statistics textbooks. So you can make a precise prediction of getting 50%, and you will see then that in that specific case, if you calculate 1/2 to the power of 10 and multiply it with the right binomial factor, you will get a very small probability with only 10 tosses, okay? That's a very small probability of you getting a perfect fit. Now, if you look at the formula below here, if you say at least 50%, then when you increase n, this probability gets larger and larger. And if you do 10,000, then the probability of you getting 90% or 91% is actually pretty high. So the probability increases with the number of samples which you include. And you will see that demonstration here if I run a code. And so let's go back to the Jupyter notebook. Let me just bring that one up. And let's set up that one for those of you which are online as well, so that everybody sees it correctly. Here we are. So if we now look at the tossing the coin here, we have this voting classifier is actually based on this philosophy of tossing the coin. But what you could do now with a voting classifier is that you could bring many methods together. So you could do a classification problem with a neural network, logistic regression, with support vector machines. You could do it with any other method, and then you would simply pick the average of these methods, and that normally improves the quality of the result. That means you narrow down the error. This is very important. So if I do the coin toss and I do it, let's say, 1,000 times, and then I do it 10,000 times, my error in the prediction of having 50-50 is getting smaller and smaller. You're probably familiar with something called polls of polls. Have you heard of that? So you have many opinion polls, and they often give slightly different results. So polls of polls uses actually what you might call a voting classifier. And then it narrows down if you take the average of many different measurements or many different opinion polls, then it simply narrows down the error in the prediction by taking many different methods. So this is the voting classifier. And if you go to scikit-learn, that has actually baked this in. A simple example, which we're going to see now, after we have looked at some of the general properties of these methods. So we are going to look at first bagging and random forests. We are not going to spend so much time on voting classifiers because they have become less used. The methods which are really the most popular ones are the boosting methods. And gradient boosting is really the favorite methods. And sometimes it does much better job on smaller data sets than a neural network does for us. So the method which we are going to encounter is actually bagging, which is easy to make. You can make it yourself by using the bootstrap. So this is aggregation by bootstrap. And what you're doing now is you're just making a forest of the same trees. We'll be coming back to that. And then the same tree feature is compensated by random forests. These are normally methods from experience which lead to a smaller variance and a smaller error. These are methods which can avoid overfitting with a typical decision tree, whereas boosting method can easily overfit, but they can also be shown to reduce the bias and variance. And these are some of the, the pre-deep learning revolution methods. So random forest and boosting methods came around 2000, and they are extremely popular and they are easy to implement. And they can be understood intuitively. So if you have a code for splitting the tree, like this Gini index we discussed last week, or the entropy, then you can use a decision tree as a basic element in all these other methods. But let me give you a quick presentation of this voting case. So this voting case, the idea behind boosting and voting, for instance, can then be rephrased as follows. Can a group of people somehow arrive at highly reasoned decisions despite the weak judgment of the individual members? You may ask whether the result of the American election is a result of a voting practice, but that's another discussion. But the aim is then to create a good classifier by combining several weak classifiers. That's if you keep track of this wording, weak classifier, this is the essential element. So you have a shallow tree, for instance. So when we think of a weak classifier, it's slightly above predicting correctly at the level of 50%. That would be a weak classifier. If you predict at the level of 50%, it means that you can equally toss a coin, right? But a weak classifier is something which performs better than just tossing the coin. And it's easy to train, which means that you don't use that many cycles. And all these methods, they try to improve upon the quality by improving the weak classifier in one way or the other one. So a weak classifier, as I said, is a classifier or a regressor method, which is able to produce results that are only slightly better than guessing at random. The basic approach is to apply repeatedly. And in boosting, this is done in an iterative way, as you will see pretty soon, a weak classifier to modifications of the data. In voting, on the other hand, you simply apply the law of large numbers, while in boosting, we give more weight to misclassified data in each iteration. So these are some of the basic features of these methods, and we are coming back to the mathematics of especially boosting methods. So boosting methods are extremely popular, and what you typically do in the iteration, where you improve upon your model, you give larger weight to the misclassified numbers. So if you look at this tossing the coin, this is a case which of a so-called voting ensemble. And you can think of yourself tossing coins with a biased outcome of 51% and 49% of tails. So with only a few tosses, you may not clearly see this distribution, because if you do 10 times, you may get 8 times with head and 2 times with tail. And then you repeat it, and then you may get another distribution. But when you do this many, many times, then what you would get then is something which looks like what we have here. So if we do this simple voting example, here you can now see that this is the number of coin tosses. And if I have this bias towards 51%, so now I didn't give it a 50-50 case, but I gave it a 51% case. So what you're seeing now is that when I increase the number of coin tosses, my error in the prediction, so the different lines are different starting points. So you can think of these different colors as different experiments, where I started with one type of random number, and then I generate a sequence of data, and then I keep increasing the number of coin tosses till, as you can see here, when you get to 10,000, you will get a very small error in the prediction around 51%. This is basically the philosophy which you have behind polls of polls. So you take all the different companies which deliver opinions, and then you simply take a voting classifier and use that one to make the best possible estimate of the error. So some of these results are pretty intuitive, right? I mean, more experiments and using the binomial distribution, you would be there. I'm going to skip this voting classifier, but you can actually see in scikit-learn, you do have a so-called voting classifier. So in this example here, I'm actually taking logistic regression, random forests, and there's also a support vector machine, which we haven't discussed this year. And these are 3 methods which I use for classification. And the data set which I'm making now is something which is also included in scikit-learn. It's called make moons. It's a binary case, so it makes circles and triangles. And these are the data set. And then you have to distinguish between circles and triangles. That's the make moons case. And the voting classifier here takes these different estimators. So it takes the logistic regression, the random forest, and the support vector machines. And voting hard means actually that it takes just a majority vote. And in this specific case, we set up the training and calculate the score. And you will typically see now that the different methods by themselves in the classification on whether you have circles or triangles in the data set, the different methods are not actually doing that well on test data, but then you have the voting classifier, which now does the majority vote of these methods. Now, after the break, so this is actually a type of methods which are less used now. And also let me just run through these before we take a break now. The methods which we are going to look after the break are actually these so-called bagging methods. So this is the first attempt of making a forest of trees. And this is something which we can easily code ourselves by using the bootstrap programs which we developed in connection with the linear regression case. So the thing you're doing now is simply to grow a tree with more and more complexity as a function of the number of bootstraps. So every time you do a bootstrap, you make a new tree. The problem, however, is that since the tree will be dominated by one main feature, these trees will all be lookalikes, because when you train a given tree, it will be dominated by the main feature, the dominating feature. So that means that the root node will look the same of essentially all the trees we make. And that is a problem which can easily lead to overfitting as well. And it makes a homogeneous forest. So after the break, we are going to look a little bit in how we can make our own bagging method. Then we will move from bagging to random forests, which is an extremely popular method. And then at the end, we are going to start with boosting methods. And this will also keep us busy next Monday, when we also summarize the course. So as I said before the break, many of these methods are very intuitive. And bagging is one of these methods where we actually reshuffle the data like we did with Bootstrap. So in the code example, which you will see now, we are actually going to bring back the code which we analyzed when we did the Bootstrap for linear regression. But now we are going to use that one on a linear regression case with trees. So you will recognize some of the functions which you have seen before. So let's try. So bagging is simply us doing an aggregation of trees. So bootstrap aggregation, and that's translated into bagging. So sometimes you ask yourself, where do people cook up these names actually? And bootstrap is also, why do we call it bootstrap? Right? So it's there's actually a long legend behind that. I can tell more. I can say more about why these methods are called bootstrap a little bit later if you're interested. So the method actually improves accuracy of a single tree. However, what happens is that since you now are making a forest of trees, this kind of interpretability which you had with a single tree is lost. So you're going to get a better fit, but the way you interpret data via a simple tree which splits into internal nodes and leaves at the end, that interpretability is lost. So there's always a trade-off when we want to improve upon accuracy, because that means often that we make a more complex model. But you would now use a tree as your learner. So if you now look at this model, you remember this function, e to the minus x squared. This was a function which we used in the linear regression cases. So what we are going to do now is to simply say that we want to make a tree with 100 points. So we want to fit this function with 100 points. And we are going to reshuffle this data with a replacement 100 times. So we do 100 bootstraps. This means that for every tree, or every data set we have, we are going to make 100 trees. So 100 bootstraps means simply we make 100 trees. So every time we do a bootstrap, we have a new data set, and then we train a tree on that. See the basic philosophy here? So if you then look at what we are doing, I'm just setting up I'm actually using this as a way to perform a bias variance trade-off as well. So I will calculate the mean squared error for that function with different decision trees. And I'm going to calculate the variance and the bias to see if I'm overfitting. And I'm going to apply this on the test data. So you see again, everything here is as before. So we are doing the classical test train. We are going to import, we are scaling the data here, simple scaling. But then we compare this also with a simple tree, which is a decision tree of max depth equal to 3. And you can see here that we are now going to have trees which have a max depth of up to 8. So the variable max depth, which you see on the top here, is my decision tree with up to 8 internal nodes. So this is my basic model. And you see that I'm calling this decision tree regressor. That's the model. And that has a given depth. So the complexity of my model is given by the depth of the tree. So instead of having a polynomial fit as we had in the very beginning and also in project 1, the complexity of the model is now given by the depth of the tree. The deeper the tree, the better we are supposed to fit the data. So if we run this case, so let's just run it and see what we get. You will see something like this. So this is now the depth of the tree, which you have along the x-axis. So we go up to depth 7 here, and then we look at the mean squared error, and you can see that that is seemingly flattening out now. So it means that if I have a tree at roughly depth 4 and 5, I'm getting something which now gives a good bias and a good variance as well. So for this type of data, if I am happy with a mean squared error of, let's say, 10 to the minus 2 or something like that, then this is a model with a given complexity which now shows a mean squared error which we probably can live with. If you're not happy with it, we would have to increase the complexity of the model so we can make the trees deeper. So let's just keep this number of points and train it with a deeper level and see what happens. Now I need to find my pointer here because that disappears. So here we are. So let's do a depth of 14 then and see what happens. And now you see that the mean squared error is still pretty flat up to roughly 10, 11, 12, but then it starts to increase. So this is a typical signal of overfitting. What we have done now is to grow a tree with up to a depth of, actually it is 13 here because I have 14 minus 1. And we are calculating the bias and the variance and the mean squared error. And we are growing a forest of 100 trees. That's what we are doing here. So this is a forest of 100 trees. And the thing is that when we make a forest of 100 trees like this, they are all going to be lookalikes. So this is going to be a homogeneous forest of fir trees or birch trees or whatever is your favorite tree. So to compensate for that, what we normally do, and this is something which gives us a better model normally, we're actually going to fit a tree with less features. So random forests, they normally provide us with a model where we, instead of training the tree with all the features which we have, so suppose you have 30 features like the cancer data. Now what you do now is simply to reduce the number of features randomly. So suppose if you go back to the cancer data, we found that this worst perimeter was the most important feature. Now we select randomly, let's say only 10 of them, and then we grow a new tree. In that way, we are going to make trees which are less correlated, because when you grow a forest with the same trees, they will basically have the same root nodes. And there will be strong correlations between one tree and the next tree. Here, we are actually making a forest now which contains different trees, and hopefully then there is less correlations among the different trees which we are setting up. And what we do now is we build, again, a number of decision trees on bootstrapped training samples. But when building these decision trees, each time a split in a tree is considered, a random sample of a given predictors is chosen. And as you split candidates from the full set of P predictors or features. So think back to the cancer data. You have something like 30 features. Now we could take the square root of 30, just to give an example. This is a pretty common rule of thumb. So the tree will be more shallow. It will have less features. But then the hope is that they are less correlated and that can increase or make a better prediction. So each split in the tree, the thing is that we are not allowed to consider the majority of the available predictors. So the reason for that is that if there is a strong predictor in the data set, along with a number of other moderately strong predictors, that predictor, if you take all features, that will dominate in the construction of the tree. So if you go back to that grade example, the grade trend was a strong feature. That was the one which was dominating. So if I were to make bootstrapped trees without reducing the number of features or selecting them randomly, then the grade trend would be dominating all the time. So the algorithm is also extremely simple. You can grow a tree of, say, B trees, and for every tree here, you draw a bootstrap sample from the training data. So you're using bootstrap as we did before. So we have these 100 data points, and every time you grow a tree, you bootstrap it, the data set. So that means that the data set you feed into every tree will be slightly different. So again, this is this kind of poor scientist way of gaining more data. And the next step is you grow then a random forest tree based on the bootstrap data by repeating the steps which you follow here. So this should actually be an inset here. You select m less than p variables. Normally you select m to be the square root of p, and p is a number of features. So if you go back to the cancer data, the Wisconsin cancer data, that would be the square root of 30, and which gives you roughly 5 features. Then you pick the best split point among the m features using, for example, the CART algorithm, which is the most common algorithm for making the tree. And when you've done that, you create a new node, and then you split the node into new daughter nodes, and then you output the ensemble of trees and make predictions for either a regression type of problem or a classification type of problem. And if you want to use a classification type of problem, so here we have some examples where we use the bagging classifier. So scikit-learn has all these different methods included. And if you scroll down here, you will also see how you can use the random forest classifier. And in this case, we are using 500 trees, and we use the entropy as the way to make the splitting. So you can replace entropy with Gini factor. So these are options which you can have when you're setting up a decision tree here. And as I said, if you want to, and there's always been cases every year where people have written their codes themselves for project free. This is an option, but many of these codes are well set up with scikit-learn. And to set up this kind of splitting and grow the trees, as you saw with the bootstrap code, is not that, or the bagging code is not that difficult. But feel free to study trees if you want to. So we can run this example here, and you will see now that the test accuracy with logistic regression with scale data is not that bad. But you see now the random forest is doing much better. So we are actually on the Wisconsin cancer data, we are getting a pretty good hit here with 98%. And you see also that the misclassified, the true negative and the false negative ones are only 2%. And so random forests do actually often perform better than many of the other methods. But now we're going to take the step into a class of methods which does even better than random forests and bagged trees. And that is the class of methods called boosting methods. But you can see here that the random forest does a pretty good job compared with some of these other methods. So we had the singular, the support vector machines, which is a method we haven't discussed this semester, which gives a 96%, the same with logistic regression. So this is actually not that bad. And the curves, the cumulative gains and ROC curves look pretty nice. So recall then that the cumulative gain shows the percentage of the overall number of cases in a given category gained by targeting a percentage of the total number of cases. And then this receiver characteristic curve or ROC curve, that displays the diagnostic ability of a binary classifier as its discrimination threshold is varied. It plots the true positive rate against the false positive rate. So these are different ways by which you would, let's say in project 3, and many of you did that in project 2 as well, display the results of a classification case. Now, what we are going to do now is to go into the final method we will discuss this semester. And we will also sneak in the first lecture next week, next Monday. We will end the boosting discussions. And then the last lecture will be a summary of what we have done. But I wanted now to jump into the whiteboard, if that is okay. And then we are going to look at the mathematics. And the reason for that is that here we have, if you think of the previous methods, these previous methods are very intuitive. And when you have a tree, what you're essentially doing, you're aggregating trees in one way or the other one. What we have not discussed is actually the statistics behind these models. That is a little bit beyond the scope of this course, but we have a course which is called SDK IN 4300, where they actually discuss in more depth the statistical data analysis of boosting methods and this bagging and random forest methods. So this is something which we have not discussed in this course, and we will leave that, but simply refer to the literature and say that if we go back to what you saw here, there are things which we won't have the time to cover properly, and that is a discussion of, if you look at this here, how it handles overfitting and reduce variance. These are topics which we have not discussed in depth here. So I'm simply stating that these methods are methods which behave favorably. They're very easy to program, and the mathematics is extremely simple. So the way we make a tree, that is the basic ingredient in all these methods. These are also the basic ingredients when we now move to boosting methods. So let's switch now to the boosting methods and stay in the whiteboard for the rest of the day today. So when you dive into these methods, there are two basic methods here. One is called ADA boost, and the other one is called gradient boosting. Gradient boosting, if you now go into different articles and so on, you will often find that referred to as XGB. X for extreme and GB for gradient boosting. But the XGB is just a library which implements gradient boosting. And it implements it in a very efficient way. And the application of XGB, which you will find examples of in the Jupyter notebook, this is one of the methods which really beats many deep learning methods in these competitions which you will find, for instance, on Kaggle. So it's an extremely popular method. So what we need to do now is simply to try to understand what is the mathematics behind these methods. So let's try to demystify. And we are going to start with the ADA boost. So this is where we start now. But the basic idea here, so the basic idea is to use a weak learner to train continuous improvement in an iterative way. So let me write this down. So the basic idea is to use a weak learner to train continuous improvements and the idea is actually very ingenious. So you train continuous improvements in an iterative way. You can use this for both regression and classification. Now, ADA boost, the way it has been presented in the literature, is mainly applied to classification. But we will start with just a plain regression case, because that hopefully will develop your intuition about these boosting methods. So how would we do the first elementary step? Now, what we are going to do now is that if we are looking at a regression case, which often, at least for me, feels like the simplest case, what we are going to say now is that there is a function f of m of x, which is going to approximate the function y of x. And y of x is our output. This is part of the data we want to train. Now, what is this f of m? Now, f of m, in one way, so one possible way of setting this up, so one possibility, possible setup, and you will see that this changes when we go to classification. One possible setup is to assume that there is a function f of m of x, which is something we will train in an iterative way. So we start with m equal to 1, and we go up to m. We have a parameter beta m, and then we have a function b of x, and this depends also on a parameter gamma of m. So b of m is a parameter, or beta of m. This b, which we have here, is our weak learner. And this gamma is also a parameter. So we want to optimize these parameters so that this function f of m becomes the best possible one. So the kind of model which we are going to have now is a model where we are going to set up this f for a given value of m of x, which is equal to a previous value of m minus 1 of x, plus these parameters beta m, multiplied with this function of x, given by a parameter gamma of m. So it's typical. You can actually start this f of 0 of x is an initial guess, and sometimes you can just put it to 0. So it could be 0. And the idea then is to use a simple function. This could be a linear function. So I could take just a straight line, which has then only 2 parameters, and then I would train these parameters iteratively. So my hope then is that the function which I'm getting at the end becomes a better and better representation of the final data. So this is the essential philosophy of these kind of boosting methods. So you're boosting a crappy thing. That's what you're doing. You're coming there with a bad old car and you're trying to boost it up and try to make this look better and better. Now, these methods are extremely powerful because the training then is applied to a method or a function which is easy to train. So the hope then is that by these gradual improvements that you will get a better and better result. So let me show you an example of how this could actually look like. So let's take an example with a simple function which we call a b of x of gamma. So now we are not specifying the specific parameter, but this could be given by 1 times gamma times x. That's the function we want to train. So we are going to use this function again and again to fit a model. Then we need to define a cost function. So we will define a cost function, a cost or loss function. And obviously, in our case, since we're doing a regression problem, it feels natural to use the mean square error. So we are going to define a cost function, which is going to be a function of this f. which is the model we are making here. And that could be simply the mean squared error, where we now are defining a loop over all the data points which we have. We have the target values minus, and then we are going to have this function f of x of I squared. And this f of x of I is now something which is solved iteratively. So in our case, this is going to look like as follows. So it's going to be 1 over n, and I'm going to have a sum from I equals 0 to n minus 1. And then what I'm going to have now is this function for every m, little m, up to a final m, I'm going to have a y of I minus, and then I will have this f of n minus 1 of x of I. And then I'm going to have this minus, and then this parameter beta. I haven't defined beta yet, because I'm going to use a minimization problem to do that, plus gamma of x of I, and this is squared. So what I plugged in here is simply this function f of m of x of I. But then I need to determine, so we must determine beta and gamma. So the optimization now for every value of m, every single value of m, is us calculating the derivative of that specific function. So what we could do now is to make a guess for the initial value, f0 of x. So if it's okay, if I can shift page here, it seems that everybody has written it down. So I could now use my guess, which is just f0 of x, and I just put that one to 0. And then I look at m equal to 1. Then my function f1 of x is going to be equal to f0 of x plus this beta 1, which is undetermined, times this function b, which is a function of x, and this gamma 1, which is undetermined. So that means that what I need now is to find the derivatives. So we need the derivatives of this cost function of d of c, of d of beta, and we are going to put a beta m here, and the gradient with respect to a given gamma of m. So for the first value of m, so we are going to repeat this till we reach the uppercase letter m value, which is the number of iterations we are willing to perform. So this b doesn't need to be the simple function which we chose. It could be a decision tree for regression problems. So we could actually replace this b, then the parameter gamma, which you would have there, would then be the depth of the tree. But let's stay with this simple problem here, because then we know that if I calculate now my dc of d beta 1, and we want that one to be 0, then it's simply me taking the derivative of the function which you see here. So if I take the derivative of that one, what I will be getting is simply minus 2 divided by n, and then I have this sum over I equals 0 to n minus 1, and I'm going to get the function which I have. So I'm going to have a 1 plus gamma 1 of xi, and this is multiplied with y of I, and then I'm going to continue on this next line, minus f of 0, which I put to 0, minus, and then I have my variable beta of b of x of I of gamma of 1. So this is b of 1, like that. That's this derivative. And now you see that when I take the next derivative with respect to gamma, we are going to get a set of nonlinear equations. So we will not be able to find an analytical solution to these parameters. And we have to solve them by gradient descent. So that's the way we would calculate these gradients and drive them to zero. So what I would get next is an equation for dc of d gamma 1. Now this is a gamma, sorry. And that gives me simply minus 2 divided by n. And then I have my summation over I. And if I look at my derivatives here, if I go back to the function, the simple function which I chose simply tells me that if I take the derivative here, I'm going to simply to have x of I here. That's the only one. If I take the derivative with respect to that one, so I will get then an x of I. In this specific case, I will have a beta 1 of x of I multiplied with yi minus f0, which we actually did put to 0, minus beta 1 of 1 plus gamma 1 times x of I. So that's the next derivative. And then the optimization. So this actually gives us a set of nonlinear equations in the unknown parameters. And this is something which we have to solve by gradient descent methods. So solve, and we obviously want this to be 0. So this is solved by gradient descent. So then you would include a learning rate, etc., etc. So in general, if you're setting up the algorithm here, you would then set up an algorithm like this. So you need to define a cost function, algorithm. So we would define a cost function, loss or cost function. We need a data set D, which now contains these different data which we want to reproduce. yn minus 1. We need to define a weak learner. Which we call for b of x, and it's a function of this variable gamma. And gamma, as I said, if you're dealing with a decision tree, so this function b is something you defined. Actually, the power of these methods, as you see them now, if you look at the algorithm, the power of these methods is you including the gradient descent you have developed earlier, and then you simply need to define a weak learner, which you keep training. So when you now have defined these different functions here, you need also to define the number of iterations. Which we label as this uppercase letter M. And then what we would do then is the following. So 4, and we also need to define an initial value, f0 of x equals something, initial value. Normally you put it to 0. So then you would have for little m equal 1 to m. The first thing we do now is to minimize. So we would then find the optimal parameters for a given gamma m and beta m, the optimal values. They will simply be given by argmin of gamma m and beta m. These are the parameters we are sticking in here of, and let's just continue on this line, of a cost function which depends now on y and this function f of m. When we have that, with this minimization gives gamma m and beta m. Then define the new function, new f of m, which is going to be given by f of m of x, given by the previous value, minus x, and then plus this beta m, the optimal value, and then we have this function b of x of gamma m optimal value. And then we continue till we have reached the final iteration. So clearly, after you've done that, you would then assess whether this is a good model or not by calculating, let's say, the R2 score, the mean squared error, or other types of scores which are important for that type of problem you're dealing with. But you see the simplicity of the models here. So if I'm dealing with a regression case, I need to define a cost function. I have to find a weak learner. So you could actually implement this very easily, this type of regression problem, with all the material you have from project 2 and from project 1. So you could try to fit a more complicated function by using just a straight line and then keep updating it. The whole thing with these methods is that they use weak learners, which are methods which barely give us something better than just tossing the coin if you're dealing with a classification case. However, they are easy to train. And by gradually improving upon it, the hope is obviously that you get a model which is better and better. So this is the basic philosophy of boosting methods. So you boost something which is crappy, and you keep increasing the quality of it, hopefully. Any questions? Does this sound okay? Okay, so what I'm going to do now is to look at the classification case, because there's a famous algorithm which is called ADA boost, adaptive boosting. So let's look at the classification case. So the regression case is actually something which you don't need to do a regression tree. You could take a well-known function which perhaps does a good fit to your data. Now, one of the reasons why people use decision trees is that a shallow decision tree is easy to train. So at the end, you're always looking at the number of CPU cycles you want to spend. And training a decision tree is something which, if it's shallow, not very deep, then it normally is something which is quick to train and use in a complicated data set. So let's now look at the adaptive boosting, or ADA boost. So we switch now to the classification case. And there is a famous method which is called ADA boost. And my claim, as it was with the regression boosting, is that these are codes which are easy to implement. So you need your gradient descent to train the gradients, and you need to have a weak learner or simple method. But let's now look at one of the ways we can do a classification. So we are going to have a data set, D, and this is a binary output case. Y0, X1, Y1, and this goes all the way up to Xn minus 1 or Yn minus 1. And we are going to have a set where the output, each of these outputs, Y of I, is now going to be either minus 1 or plus 1. You could equally well set 0 and 1, but you will see why minus 1 and plus 1 is more convenient. You will see that from the equations which we are going to use in order to perform the classification. So this is a method where we are going to emphasize wrong predictions. So we're going to train on data which was not predicted well. This is one of the basic philosophies here. So we are going to have a set of weak classifiers And these could be decision trees. Actually, in AdaBoost and in these boosting methods, these are decision trees normally. So we define a set of weak classifiers, and this set could now be a function which I'm just going to call B1, just to stay with the previous labeling. I would have a B2 here, and this goes all the way up to a B of n. So we actually have a total of such functions, and each of them spits out either -1 or +1. So these are the classifiers. So you could think of this B as a decision tree. And when you train that decision tree on the data, it makes a prediction. So each Bj for a given set of xi, so Bj is one of these functions from m equal 1 up to m. This makes a prediction which is either -1. So this is the prediction. Each Bj predicts. So this is the prediction. So we are training a weak learner B on some data, and then it makes a prediction of either -1 or +1. So after a given number of iterations, suppose now we've done m-1 iterations. What we have then is now a new function, which I'm going to call C of m-1 of x of I. And this is going to be a function of a parameter alpha1 times this function b1 we started with. So my final function now is going to be a collection of all the weak learners I have trained. So you can then think, if I have m, uppercase M, such weak learners, that corresponds to m trees. So every such function B is a tree. So that's why we call this an ensemble method, because we are just bringing together an ensemble of trees. So that will have an alpha2 here, of B2, of x of I, and this goes all the way up to alpha of m-1 of B of m-1 of x of I. This is as before. So if you look back at what we did previously in the regression case, we had this function f, which was the sum of all the attempts we made. So let me just bring back that one so you see the parallel here. So if we go back to the regression case, you see now that what we had, like in the f1 here, this is the sum of f0 plus this function. So in principle, every such function which you see here is a function of previous. So we have this m here, and that's a function of previous trained functions. So if B's are trees, then you see also here that if I do this m times, I will have m trees. It doesn't need to be a tree. It's just your weak learner or your simple method. So in this case now, what we have is this chain of outputs. And now comes the way, how do we actually define the function we want to train? And this is actually pretty ingenious. So the cost function is now going to be the prediction error. So cost function, we want to train, is something which I'm just going to call the total error. Train is the total error, which I'm going to define in the following way, because that is going to give me simple equations to program. So I'm going to define the total error in the following way. So I run over all the data, I equals 0 up to n-1, and I look at the exponential of minus y of I. This is the data, which is either plus or minus 1, times this function c of m of x of I. So as you will see now, this is an error function. You can choose many. I could actually have taken the cross entropy, which you have seen before. But then I would have defined a slightly different function. So when it comes to the functions you train, there are many, many different ways you can do this. Why is this simple? This is simple because it emphasizes the wrong predictions. And we are going to finish this next week, but I just wanted to wrap up today. So this is a way, to emphasize wrong predictions. See? How does it emphasize? I will show you now. So let me just do that, and then we take a break. So this emphasizes wrong predictions, because now what we have y of I has to be -1 or 1, right? Then we have also decided that this Cm of x of I is giving us either -1 or 1. So we are training a decision tree, and that makes a prediction now of either -1 or +1. This is the model we are training. And now you see very clearly that if correct, then what I have is y of I times the Cm of x of I is equal to +1. And that gives me e to the power of -1. If wrong, then y of I of Cm of x of I is equal to -1. And that gives us e to the +1. So in that sum over these so-called errors, the wrongly classified, the wrong predictions gives us the exponential function with argument 1. The correctly predicted ones gives us a value of e to the -1. And that is a smaller value. So we are going to rewrite this next week in terms of some weights, because we are going to start with the first iteration, and then we have to make some guesses on what this function is. And when we keep iterating, you see now that when you multiply, if y is -1 and I predict -1, which is the correct prediction, I get plus. If y is 1 and I make a correct prediction, it's 1 times 1, again +1. Then I get e to the -1. If I do a wrong prediction, I always get e to the +1. So that means that when I'm setting in iteratively, if we go back here, this is just one error as a function of m. So every time I am improving my calculations, the quantity which will give the most weight to this error is the wrongly predicted one. So that means that when I'm going to optimize now, next week, you will see that I will find an optimization algorithm which emphasizes the wrong predictions and tries to minimize these for every new iteration. That's the essence of boosting. So that function which you see here, this error function as a cost function, is just a choice which allows us to emphasize wrongly predicted results. So next week, we are going to set up the final algorithm, and then we are also going to derive the equations for gradient boosting, which is the method which actually wins many of the competitions, and it's also very easy to implement and to understand mathematically. But the basic is that you have a weak learner, and by boosting it iteratively, you get a better and better learner, which makes better and better predictions. That's the essence of these methods. And we choose decision trees because they are easy to train. But you could have chosen other methods as well, which are easy to train. Okay, this is the overarching kind of philosophy. And then next Monday, we will try to wrap up and also discuss a little bit other things, etc., a summary of the course. And you've probably seen the weekly exercise this week is more like a summary of what we have done. And the final one, which is exercise 10, is actually a survey. So it's not going to be anonymous, but you've probably seen that we will never take revenge if you write something negative. But it's one way for us to get some feedback of how it's going, whether we are missing things and how we can improve, etc., etc. But it's not anonymous. If you want it anonymous, we can also do that. Okay. See you at the lab, guys, and best wishes for the week. And exams when they start, because some of you have exams next week, right?